In this video, we're going to look at the derivative of a function. We're going to define it, we're going to graph it, we're going to make connections between derivatives and continuity. We're going to describe three conditions when a derivative does not exist for a function, and explain the meaning of higher order derivatives. So here's how we're going to define the derivative of a function. We're going to denote f prime, or you might see it as y prime. So this is f prime, it's the derivative f prime of x. You might also see this as y prime, so you might see it as y prime. You might see it as dy and dx. dy being the derivative of y, and dx being with respect to x. We might see it as dA dt, so it is a derivative of the area with respect to time. So these are some of the notations you will see when we are looking at derivatives. The way we're going to define this as the limit as h goes to 0, where h is the distance between a given x value that we care about and another x value that is close to, arbitrarily close to. We talked about that when we were looking at the epsilon delta proofs. So as the limit as h goes to 0 of f of x plus h minus f of x all over h. So we're going to use the definition of a derivative to find the derivative of these two functions here. So first thing I want to do is find f of x plus h. So f of x plus h for this first function will be 4 times x plus h squared, which is going to give me 4x squared plus 8xh plus h squared. Now the limit as h approaches 0 of f of x plus h, which is 4x squared plus 8xh plus h squared, minus f of x, which is 4x squared all over h. And you can see that the 4x squareds cancel, and we are left with the limit as h approaches 0 of 8xh plus h squared all over h. When you get to this point, and if you don't have all the terms in terms of h, or there's an h included in all the terms, it's a factor, then you made a mistake somewhere back here. When you get to this point and you've done the algebraic cleanup, every single term had better have an h as a factor. Now what we'll do is we will factor out an h. So we have the limit as h approaches 0 of h out of the numerator, leaving me 8x plus h all over h. It's kind of like an n, but it's an h. Those h's will cancel, leaving me the limit as h approaches 0 of 8x plus h. Now we can go ahead and do a direct substitution for h, and we get 8x. Now what this represents is the slope of the tangent line. This is not the equation of the tangent line. This is the slope of the tangent line, and it's an equation. That's one of the ways to interpret it, is the slope of the tangent line. It is an equation. What that allows me to do is say for any x along this function, and the function we started out with, f of x is equal to 4x squared. For any x value that I choose from the domain of that function, I can determine what the slope is. So if I wanted to know what the slope of the tangent line is at x is equal to 3, then I would find this equation, which is 8x, and I'm just going to multiply it by 3, and so it is 24. So that would be the slope of the tangent line when I'm evaluating at x equals 3 for this function. Now let's take a look at my next equation. It's a little bit more interesting, my next function. So I'm going to do this in blue. So the limit as h approaches 0. In this case, I'm not going to find f of x plus h first. I'm just going to go ahead and do that as I define using the definition of the derivative. So I have x plus h plus 1 over x plus h minus x plus 1 over x all over h. Now I have multiple fractions in this expression, this being the expression right here. I have multiple fractions. I have this fraction, I have this fraction. So what I'm going to do is I'm going to combine up like terms that I can, and then I'm going to get rid of the fraction. And what I mean by that is I'm going to go ahead and take these parentheses off right here, and I'm going to distribute this negative through on the x and the 1 over x, and then I can take these parentheses off as well and just kind of clean it up a little bit. So I have the limit as h approaches 0. Now, this x plus h and this x, once I distribute the x, will cancel themselves out. So I'm just going to be left with h plus 1 over x plus h, and then a minus 1 over x all over h. Again, that's because this x, and when I distribute this negative through, this x will cancel. And then don't forget to distribute the negative on the 1 over x. What I'm going to do now is I'm going to go ahead and multiply everything by, and I have some problems here. Okay, I'm going to go ahead and multiply everything by the x plus h and the x, because that is my lowest common denominator of all the fractions that are here. This is over 1, this is over 1, so these two multiplied together will be my lowest common denominator. So I'm going to multiply the numerator by x plus h to clear out those complex fractions, and then I'm going to multiply the denominator by this as well. When I do this, I'm going to get the limit as h approaches 0, and I'm going to have h times x multiplied by x plus h. That's my first term, plus my second term, the x plus h's. So when I do this multiplication, the x plus h's go away, cancel out, giving me just x. And then when I do this multiplication, my x's cancel, leaving me minus the x plus h. And I'm going to go ahead and put the x plus h within parentheses so as not to forget to multiply the negative 1 through. I'm going to go ahead and clean this up a little bit algebraically. So I'm going to leave out the x and the h. I'm not going to distribute it through the x plus h, because my goal, remember, was to get to the point where every single term, I forgot here, the x and then the x plus h in the denominator. My goal here is to make sure that every single term has a factor of h in it. So it's really just these last two terms, to begin with the x and then the minus the x plus h, that I'm going to worry about, because the only thing that doesn't have an h attached to it at this point is this term. So when I distribute this negative through, these two x's will cancel. You can see that those two x's will cancel. And so I'm just going to go ahead and erase that, because those two will cancel, leaving me just a minus h. Now every single one of my terms has an h, so I can factor that out. So the limit as h approaches 0 of h, I'm going to factor the h out of every single term. So I have x plus h minus 1 all over, and why do I keep forgetting that denominator, x plus 8, or xh multiplied by x plus h. And here you can see my h's cancel. That leaves me the limit as h approaches 0 of x plus h minus 1. Now, notice, and this is kind of a pain to continue to write this unless you really like to write, notice how I have to keep writing the limit until I'm actually ready for the direct substitution. If at any time when I'm doing the limit as x approaches, or as h approaches 0, or any limit, until I'm actually ready to do the direct substitution, if I drop that notation, it is not mathematically correct. So I will be paying attention to that when we are looking at your tests or homework or quizzes. Now I'm finally ready to do the direct substitution, and when I do the direct substitution, and this is all over x plus h, why do I keep dropping that denominator? I don't know. So when I do the direct substitution, I am going to have in the numerator, I'm going to have x squared minus 1 over x squared. Now I can clean this up, because what will happen when we get into derivatives, you're going to see this as this 1 minus 1 over x squared. And that's going to be more familiar to what we're going to see when we start to use our rules of derivatives. Okay. So we say a function is differentiable at some point A if f prime of A exists. So in other words, if A is part of the domain of f of x, it is differentiable at that domain value if the derivative actually exists. More generally, a function is said to be differentiable on an open set S if S is differentiable at every point in the set, and differentiable function is one in which f prime exists for every value on its domain. That leads us to this first theorem. Differentiability implies continuity, but not the other way around. So you can be continuous, but not differentiable. Just want to say that now. You can be continuous and not be indifferentiable. So here's a graph. Here's actually 3 different graphs. In these 3 different graphs, you can see that each one of these graphs are continuous. It's continuous along this curve, it's continuous for the absolute value, and it's continuous for this piecewise function. Now, the reason this is not differentiable on its entire domain is because we have a vertical slope right here. So at this point, we have a vertical tangent line. And so that means that it's actually undefined at 0. The other thing that has to happen for us to be differentiable, so it has to be a smooth curve. This is not a smooth curve. So this is also not differentiable. Now, if we were to zoom in really close on this, we're going to see oscillations here. So this is not differentiable here as well. So these are the things that tells us when we're not differentiable. If there's a sharp corner on the graph, absolute values is one of them. If the graph of the function has a vertical tangent, we showed you a picture of that. If the slopes of the secant lines continuously change direction as they approach A, that was our oscillation. And of course, if it's not continuous at that point A. So here we're asked to determine the domain of the function. Then graph the function and determine if the functions are differentiable on their domains. And if they are not differentiable on their domains, determine whether they are not differentiable. Determine where they are not differentiable. Excuse me. Now this, we know, is the same thing as a cube root. So this is the same thing as the cube root of x plus 1, the quantity squared. Now, because it is a cube root, we could have ended up with negative numbers, but in this case we won't because of the fact that we have this squared term, so everything will be positive, but it would have been okay if we would have had a negative number underneath the cube root. So for this first function, our domain is negative infinity to infinity. So there's no place in which that is undefined. And if we look at b, this is the same thing as the cube root of x raised to the 5th power minus 2 times the cube root of x. This also has a domain from negative infinity to infinity. So the domains are defined for all real numbers. But the question is, does either one of these have an issue with the graph having a vertical tangent or a sharp corner? So what I'll need to do is I'll need to graph these. So I can graph these by hand, or I can go out to Desmos. So I'm going to just go ahead and go out to Desmos, and I'm going to graph this first one. And this is what the first one looks like. Now, even though it is defined everywhere on its domain, it has a corner right here. I have a corner right here. Now you're thinking, how am I supposed to know that without a graphing calculator? Well, I will give you, if I ask you questions about the locations, I'll give you the graph. in which this is undefined for its domain, for its derivative. So we have no derivative here. So at this point, x equals -1, we have a corner. So even though I can do the derivative of this all day long, I can't actually do any evaluation at x equals -1 because it's not defined for its derivative at that point. It's defined on its domain, but it's not defined for its derivative. So let's go ahead and go out and graph the other one in Desmos. And here is that graph. And you can see the graph of the second function here has a horizontal tangent at x is equal 0. So even though we can do the derivative for this all day long, we won't be able to evaluate it at x equals 0. Now, what do higher order, let me move all this out of the way. So what do higher order derivatives mean? Well, as we think of, if we think of f of t as being the position, and it's in, say, meters, then its velocity, we know from last chapter, is going to be meters per second. We found the average velocity, then we found the instantaneous velocity. And when we were doing that, we were doing basically derivatives when we were asked for the instantaneous. So that's a velocity, which is meters per second. So its first derivative is velocity. The second derivative is acceleration, and its third derivative is jerk. And a little bit of tidbit of information, higher after jerk is snap, crackle, and pop. Go look that up. It's kind of cool. So we can find the derivatives until either we reach 0 or until we get bored, because sometimes the derivatives will just keep going back and forth. Trig functions are one of those ones, like sine and cosine. Derivative of one is the other. So we can continue to take the derivative of sine or cosine until we're just bored, or until we get to where we need to be. Now, when we're doing the derivatives of higher order, we want to think of this as this notation. So here's my second derivative, my third derivative, my fourth derivative, and my nth derivative. We can do it this way. We can do it with primes, so we can do y prime, y double prime, y to the fourth, y to the n. Or we can use this notation. Now this notation is the second derivative of y with respect to x, the third derivative of y with respect to x, the fourth derivative of y with respect to x. So when we see this, it doesn't matter what the numerator is and what the denominator is, it's telling us we have some function, whatever that variable is, in terms of the other function, and that's how we're going to do the derivative. So if I'm asking for the area is pi r squared, then my derivative would be dA with respect to r. So I'm taking the derivative of the area with respect to the radius. And if I wanted to do the second derivative, it would be the second derivative of a with respect to r twice. So it doesn't matter what we are using as variables. The one that is on the variable by itself, that's the one that goes in the numerator. The one that is not by itself, think of it as our input. Our domain value is the one that it is with respect to. The one that is solved, that is our output, is our range value. So we can use a's and r's, we can use y's and x's. It just depends on what our variable is. So using the definition of derivative, find the equation for velocity, acceleration, and jerk. So let's go ahead and do that for these equations. So we're going to do it to the fourth power first. We're going to find my velocity, so f prime of x, which is the velocity. And this is going to be equal to the limit as as h approaches 0, of x plus h raised to the fourth power minus f of x, which is just x to the fourth power, divided by h. And we'd go through this process. Now remember, we know the binomial theorem from pre-calculus 2, or you can use your Pascal's triangle. So what I'm going to do is I'm just going to give you the answers, and I'll let you take the opportunity of going through these. So f prime of x is going to be 4x to the third. F double prime of x is going to be 12x squared. And f triple prime, which is the jerk, is going to be 24x. The same thing here, we're going to do the velocity, which is d prime of t, which is the velocity, which is equal to the limit as h approaches 0. In this case will be x plus h raised to the third power plus x plus h minus my original function, which is x cubed plus x all over h. And so d prime of t, I'm just going to give you the answers here and you can check them. So 3x squared plus 1. D double prime, which is the acceleration, is going to be 6x. And d triple prime of t, which is the jerk, is going to be just 6. And if you want to go over any of these in class, we absolutely can. Let me move all of this up and out of the way. So let's talk about the graphs of the derivatives. So we're now going to start in this chapter. We're going to be graphing functions, and we're going to be graphing the first, second, third derivative. There's a couple of things that are going on. So whenever the tangent lines have slopes of 0, f prime have x-intercepts. Well, where would the slopes have 0? Well, that would be when I'm at a maxima or a minima on my graph. So I have a turning point. Whenever I have a turning point, my derivative graph will be crossing the x-axis. Maybe actually bouncing, touching and bouncing back off, but it is going to the x-axis. Where the slopes of the tangent lines are positive, then my derivative graph must be above the x-axis. It must be greater than 0, and that makes sense. Because when we are doing the graph of the derivative, we are graphing the slopes of that function. Where the slopes of the tangent lines are negative, then my derivative graph will be below the x-axis because they're all negative. With that information, let's take a look at this piecewise function. Now, this is a line, so the slope is the same, so its derivative should be a constant. Notice how this line is a negative slope, therefore its derivative is a horizontal line below the x-axis. And if this slope is a -1, then this horizontal line for the derivative will be at -1. Notice because these are corners that both of these are open dots on the derivative because it is not defined at those corners for the derivative. This slope is positive. This line has a positive slope. This is piecewise, so this piece has a positive slope. And it's the same, so it's a horizontal line. So this horizontal line, this represents a horizontal line as its derivative, and it has a slope of 1. This has a negative slope, so this piece of the piecewise function has a negative slope, so it is below the x-axis. It is a horizontal line because this slope is the same in this entire region. So it's a horizontal line at the slope of -1/2. So if we are giving these functions and we're asked to graph the derivative, let's talk about what's happening. This function is increasing the entire time. So in this entire time, these are all positive except for right here. This has a slope of 0. It's a horizontal slide, so we know that this slope is 0, but these are all positive. So its derivative graph must also be 0 at that place. Now, when I'm up here, it's a very large positive number for the slope. So that means I must be over here, up above the x-axis because it's a positive slope and a very large number. As I get closer to 0, my slope values get smaller. That means my derivative graph outputs must be getting smaller. And so it's going to look something like this. Similarly, these are still positive, but they're small numbers. And then as we get further out, these slopes are still positive, but larger numbers. And so the derivative graph for this first one will look something like that. If we take a look at B, we know right here is a horizontal slope, right here horizontal, right here is horizontal. So in those locations, I'm either going to be crossing or touching and bouncing back off on the x-axis. In this location, we have negative slopes, so we need to be below the x-axis. In this location, we are positive slopes, so we need to be above the x-axis. But remember, we have to come there, so we have to come and touch and bounce back off. All of these are positive slopes up until I get to this point. So all of these will be positive slopes until I get to this point, and then my slopes become negative. So let me make this a little bit better. So this is going to come, it's going to come and touch and bounce, and then it's going to come and go through and come back down like that. So that is what the slope, or that's what the equation, or the graph of the derivative looks like. Man, I took a hard time spitting that out. Okay, now right here, my slope of the tangent line will be 0 because it is horizontal at that point, maxes and minimums. Now, these are negative slopes, so I better be below the x-axis. These are positive slopes, so I better be above the x-axis, and that's what that graph looks like for its derivative. Let's talk about this last one. Now this slope is negative this entire time. The entire time, this slope is negative. But let's talk about what's happening. This is a larger negative number than this one. This is a larger negative number than the one before. And so what's going to happen in this region, this is going to be way down here, and this region is going to be way down here. This never looks like it's horizontal. Doesn't have a horizontal tangent anywhere. So it's probably going to be about right there, whatever that is, approximately maybe negative 1/8 or something. So this is probably like negative 1/8. And so this is what the graph of this one would look like. Okay? We're going to use the graph of sine to sketch the derivative of its function, the derivative of the function sine. So we know right here, I need to be crossing the x-axis because this is a horizontal tangent. We know right here is a horizontal tangent, so I must be crossing the x-axis for its derivative. We know that these are positive up until this point, so we're above the x-axis, but these are smaller numbers than this, and so it's going to look something like that. Now into this region from here to here, these are all negative slopes. We're going downhill on that entire region, so we know that those must be negative. And it looks like these are smaller values and these are smaller values than right here. So it looks maybe something like that. In this region to here, we have a positive slope. We're going uphill. These are all positive slopes. And so my graph of my tangent must be above the x-axis, or the graph of the slopes of the tangents must be above the x-axis. So it's going to look something like that. What is that? That is the cosine wave. So we know that d dx of the sine of x is equal to the cosine of x. So look at that. We were able to do that without doing much work other than graphing the slopes of the tangent lines, graphing the derivative. On this one, we're going to be asked to sketch the graph of the original function given this information about its derivative. All right, we'll start with this one. Between -2, so here's -2 and 1, the function is above the x-axis. At 2, so here's 1, at 2, our function, the derivative of our function is 0. So at 2, we must be at 0. Anything after 2, so any value for x after 2, the derivative is greater than 0. So I must be above the x-axis somewhere. At f of 2 is 2 and f of 0 is 1. Okay, the limit as x approaches negative infinity, its output goes to 0. So the limit as x approaches negative infinity, my output must be going to 0. So that's this kind of thing or this kind of thing. As the limit as x approaches infinity, my function is going to infinity, so that kind of looks like that's happening there. Okay. So let's see if we can pull this all together. Now I'm drawing in black the derivative part of the graph. So between -2 and 1, we are above the x-axis. So sure, we can be above the x-axis this entire time. And it doesn't say that I have to touch the x-axis or anything. I just need to be above it. So maybe it's going to look something like this, inclusive. So we don't know anything between 1 and 2. So I'm going to assume it implies that we are below the x-axis because it doesn't say we're above it, so we must be below the x-axis in this region. Now, the other thing is that the function itself has to go to 0. So what I'm going to do, so I don't know anything that's going on the left side of 2. So what I'll do is I will maybe make it look like this, maybe. Now, what does this mean? That's supposed to be at 2. That's really badly at 2. This should be at 2. So what does this mean for our original function? Well, let's bring together what we know about the original function. So I'm going to do that in blue. I know that at f equals 0, I have to be at 1. So I have this ordered pair 0, 1. I have to go through that. I have at 2, 2. I need to have that on my graph. So I'm going to put, here's the point 2, 2, 2, 2. I know that the original function as x goes to infinity, the output goes up forever, so I'm going to do something like that. As x goes to negative infinity, I have to approach 0, so I'm going to do something like that. Now I know right here, because I'm crossing at 1 and I'm crossing at 2, that I must have either maximas or minimas on those graphs. So I'm coming out of a negative and going into a positive. That means on my original graph here, I must have a minimum. I'm coming from a negative slope to a positive slope on my derivative graph. That means I must be at a minimum at 2, 2. Now I'm at 1 on my derivative graph, 1, 0. I'm going from a positive slope to a negative slope. That means at that point, so I'm just going to put that up there randomly, that I must be coming in to a maxima. So I'm going to connect my dots. I'm going to go through that point. I'm going to call this a maxima. I don't care how that looks, and then I do care how it looks. I don't care how pretty it is as long as it's a smooth curve and it satisfies my graph here. So now I know right here is a maxima, and up and from negative infinity to this point, I need to be above the x-axis on my derivative graph, which I am because these are all increasing slopes. At this point, I better be crossing the x-axis, and I am. At this point, I better be crossing the x-axis on my derivative graph, and I am, which implies that this must be a minimum. And it's also telling me I have to go up forever, and my derivative is above the x-axis forever after we hit 2. So I think that satisfies my graph requirements. It's maybe not be the prettiest graph, but it does satisfy my graph requirements. Okay, so now let's take a look at this particular example. With this example, the graph of the figure models the number of people who have come down with the flu T weeks after its initial outbreak in a town with a population of 5,000 citizens. Now, this is a limiting growth model, which we would have learned in pre-calculus 2. So what we know from limiting growth models from pre-calculus 2, I would recommend, if you don't remember, OpenStax book, pre-calculus, and I believe it's in chapter 5 where we have logs and exponentials. So as t increases, I'm going to get close to the number of people in this town, assuming that this town is isolated and there's only 5,000 or 50,000 citizens, none's coming in and none's coming out. So what's happening here is that these, as time moves on, you're going to get almost everyone infected, but maybe you're going to have some people that have a natural immunity, so they may not get infected. So you're never actually going to reach all 50,000 citizens, but you're going to get close to this. So the behavior as t increases, our function is going to get closer and closer to the 50,000, which means our rate of change, which is the slope of the derivative, is going to turn into a horizontal. It's going to get closer and closer to 0. So the rate of change, the number of people getting infected per day or per week, is going to go to 0 because everyone will have been infected once, with the exception of a few people. That's what that means. Now, what does the derivative tell us about this town and how it's infected by the flu? Now, derivative, of course, is a rate of change. Remember, it is velocity, meters per second. In this case, its derivative for this is going to be the number affected per week. If we take a look at these slopes, right about until about here, I'm guessing it looks about right there, and we'll actually figure this out later in this class, that these slopes are pretty steep, right? These slopes are all steep and they're all positive. So that means the increase it's increasing, the slope is increasing, it is positive, and they're pretty large. So you've got a lot of infections to begin with. And then we're going to get to this, we're going to call this a point of inflection. And we're going to learn about this later in this chapter. At some point, this point of inflection, we're still positive, we're still getting more people infected, but the slopes are decreasing. So the number of people infected per week is decreasing. So at some point, and we will work that out later in this chapter, we're going to find that point of inflection. We're going to say at this time is when the number of new cases is starting to decrease. Now, for all of us who have gone through COVID, we have seen multiple models about COVID infections, and so we are more familiar with it, and we are going to explore the calculus behind some of it. We are not going to be looking necessarily at the statistics behind it. So that's something that we have been seeing, fortunately or unfortunately, in the last couple of, years. And that's it for this video.